and form the electron will actually flow through the steel, and then the ferrous ion will go into the solution or the moisture that on top of the steel, and then on this side, which is the cathodic reaction, so the electron flow from here inside this steel and go to the other side, and this side they will mix with the water, oxygen, and then form the hydroxide ion, and this hydroxide ion will flow in the solution phase, but not in the solid phase. So this is the reason it complete a circuit. So this is the reason the corrosion is termed as electrochemical process, not just the chemical process. So what happened when at the end the passive film turned into a rust? And it has been reported that the rust volume can be 6 times greater than the original steel, which means even you put the steel so small like that in the concrete, you think that, okay, there will not be any problem when the steel turns into rust. You might estimate the volume of the rust will be same as the steel, but actually it's not, because when the steel turns into the rust is very porous. So then actually the size of the steel, the rust is 6 times bigger than the volume of the steel. So this is the reason it will impact the force to the concrete, and then they will start to expel the concrete out. And this is the reason when the steel get corroded and the concrete cannot attach to the steel anymore. So now I'm going to brief you if you have already known this, but it's okay. I'm going to remind your memory. There are different types of the corrosions. For example, the first one is intergranular corrosion, and then environmental induced corrosion, pitting corrosion. The other is de-alloy or selective leaching, or erosion corrosion, and corrosion in reinforced concrete. And another one is galvanic corrosion and crevice, microbially induced corrosion, and another is a uniform or general corrosion. Okay, let us go to the intergranular corrosion. What is meant by intergranular corrosion? As you know, the steel is not just composed of iron itself. It's composed of a small percent of the carbon, or for example, chromium also inside. So when they mix this kind of different elements together, they actually create a certain grain in this area, and then they form this boundary. So the intergranular corrosion means the corrosion will actually pass through this boundary and then start to separate the grain. And when this happens, you can see here the crack is actually follow a line like a boundary. And you can see and this is the example that I took from the publication. And when it cracked like this, actually it is an intergranular corrosion. So another one is an environmentally induced corrosion. There are two types. One is a stress corrosion cracking. Another is a hydrogen embrittlement. So what do you mean by stress corrosion cracking? As you know, when people put the steel inside the concrete, especially for the structural engineering, they will stress the steel first. Stress the steel, and then they add in the concrete, which is being called pre-stressed concrete. But when you apply the stress to the steel, so what happens is this stress might break the pressive film. So when it breaks the pressive film, and some of the aggressive ion will start to penetrate the steel. So this is the reason it causes this stress corrosion cracking. And another one is a hydrogen embrittlement. So what does it mean? Hydrogen embrittlement means there's a hydrogen enter into the crack hydrogen atom, because sometimes when they apply the cathodic repayment, because the cathodic potential will actually create the hydrogen. So this hydrogen will actually enter the crack, and this causes the steel to break into half. So this kind of break is called hydrogen embrittlement. So another is a pitting corrosion. And this pitting corrosion, when you see a surface of the steel, you see the spot like this. like this corrosion, which means this is referred to the pitting corrosion. And this pitting corrosion sometimes is difficult to be spotted by the eyes, because sometimes it can be so small, it can be hidden somewhere else. And what caused the pitting corrosion to occur is because the aggressive iron, which is chloride, and this chloride usually people obtain from the sodium chloride, because sometimes the seawater got the sodium chloride, and this might go to the building that built at the seashore, or sometimes in the cold country when they put the sodium chloride to defrost the ice, and all this sodium chloride can actually enter to the penetrate the concrete and enter to the steel. So what happens if there's a small chloride ion on the surface of this passive film, and this small chloride ion will actually break down the passive film, and then slowly it will cause this atom ferrum iron ferrum to dissolve in this one peak, and then later the chloride ion will penetrate again to go into deep inside. So you can see that, okay, it's only one spot, it's nothing. Actually, it's wrong, because when they go deep inside, they will start to cause the steel to break into half. Because inside you can see they can develop into this subsurface and very big actually corrosion inside. Although outside you see that it's just one point. And another is de-alloying and selective leaching. So what does it mean? Because in the cast irons, the engineer usually use it to build the building. They will put the cast iron inside, and because this cast iron are composed of iron and the carbon, but the carbon will resist corrosion. But however, the irons actually, compared to the carbon, the iron will actually get corroded easily compared to the carbon. So at the end, what happened is, inside the steel you will got this kind of like some kind of the hole, like a pore. Actually, it's because iron has been corroded away, and if you look at the side view, is something like this. You've got the hole, a small tiny hole on the surface of the steel. And of course, pitting is a bit more directly go deep inside the steel, but this is like a pore, because this iron atom get dissolved away. Okay, and another is erosion corrosion, and this erosion corrosion usually happen in the pipe. So what happens is, when there's a water flow here and there's a joint, they will cause a turbulence, and this turbulence will actually wash away the steel. And so when you open the pipe, you can see inside got something like this. Is because of the erosion corrosion. And another one is a corrosion in reinforced concrete. It's like inside the concrete, like I explained before, when the steel get rusted, and the rust will start to expand, because the volume of the rust will 6 times bigger. Imagine this is your steel, okay, the cross section of the steel, and then when the whole steel get corroded, which means the rust will occupy the whole volume like this. So when they occupy the whole volume like this, they will actually expel the concrete. So another one is a galvanic corrosion. What is meant by galvanic corrosion? For example, this usually happen in the nuts that you use to screw two pieces of the metal together. So when you put two different pieces, for example, one is a steel, another one is a copper, and then with time, because steel is more active than the copper, then the steel will get dissolved, and the copper will remain there. Because it gets dissolved, the electron will go to the copper. So then in this case, then you need to refer to the table called electrochemical series. That here they show you different kind of the metal. Which one, when you put them together, they dissolve faster than the other. For example, to go to the more negative one get dissolved easier, because ferrum is here and the copper is here down. Okay, ferrous and the copper. So because ferrous is more negative, have this standard electron potential more negative than the copper, because copper for the coupon to the iron coupon is plus, and this atom iron atom to the ferrous ion is negative. So this ferrous will get dissolved easier than the copper. So when you join the steel with the other metal, so you need to be careful in which position they are. Okay, if what you want is the copper to get dissolved, then the ferrous should be at the bottom. But unfortunately, because ferrous is at the top, so at the end, if you join this steel with the copper, steel will actually get corroded more easier than the copper. So another one is a crevice corrosion. So what is the difference between crevice corrosion and this one, the galvanic corrosion? Galvanic corrosion is because you put two different metal together. But however, this crevice corrosion, even you put the same metal together, but because there's a joint here, so this joint will lead to the different concentration of oxygen. When there's a different concentration of oxygen, then in this case, this part will get corroded and will go inside. When they go deep inside, this is called crevice corrosion. And this is also different from the pitting corrosion. Crevice is because of different concentration of the oxygen, but pitting is because there's an aggressive ion like chloride ion that attack the surface. So when there's a crevice corrosion, and you will see this type of the corrosion that on the nuts of your the steel, this mag of the steel. Okay, and another one is microbially induced corrosion, and now this study, a lot of people have paid attention on this kind of corrosion because they believe that the microorganism can actually accelerate the corrosion. I mean, the microorganism, they don't induce the corrosion, but they will accelerate the corrosion. And then usually the kind of corrosion that caused by this microorganism can be any kind: pitting, the alloy, erosion corrosion, galvanic, stress corrosion, cracking, and hydrogen empediment. And this microorganism can be sulfate reduced bacteria, sulfur oxidizing bacteria, or iron reducing bacteria, acid producing bacteria, even can be fungi, algae, or this Algae. And this topic is now people try to pay attention to look at it. And another one is very easy, is uniform or general corrosion. So when you see that the steel have the corrosion all over the surface like this, usually it's a general corrosion. So this general corrosion actually, they will actually attack the steel homogeneously, and they go deep inside. Okay. And now I'm going to review the composition of the passive film and the corrosion products, and what actually, for example, you see the rust here. What actually inside this rust? What's actually kind of the element that compose all this rust? So now I'm going to review all this. Okay, if you look from this, the left hand side to the right hand side, the left hand side here, first it will form passive film, and passive film normally they say that is composed of this ferrous oxide or iron hydroxide. And this I explained before in my previous slide. To form passive film, the surface of the steel will have two sides. One is the anode side, another is a cathode side. So the anode side will this iron atom will actually dissolve and form this ferrous ion and the electron. And then electron will go through inside the steel, will flow through the steel, and then go to the cathode side. And in this cathode side, the electron will meet with the water and the oxygen and form this hydroxyl ion. And this hydroxyl ion will mix with this ferrous ion. Well, when there exists a layer of moisture or the solution, and here they will form the passive film. But of course, like what I said, with the continuous existence of the oxygen or the water, and then this passive film will develop more and more to the corrosion product. And start from here, it forms the corrosion product. So it can be this Fe3O4, which is called iron oxide or ferric oxide, or called magnetite, and its a color is a black color. Okay, when then they continue, and then with the assistance of oxygen and the water, and then they will continue to develop another one, which is called iron 3 oxide or ferric oxide. And this is the color actually is like a red, but dark red color. And then continue again to form another one, which is iron oxide hydroxide or ferric oxy hydroxide. And this why here they call iron 2, iron 2,3 and iron 3, because if you refer to the oxygen, the oxidation state of this oxygen is 2. So 2 times 3 is 6. So when 6 divided by 2 for this ferrite is like the oxidation state of ferrite is 3. So this is called iron 3. Okay, start from here, it's called iron 3. But here is iron 2 is because the oxygen state of oxygen is 2, is -2. When they give to this ferrite is also 2. But here is somewhere in between, because you can see this oxygen state of the oxygen is 2, and 2 times 4 is 8. Later 8 divided by 3 is somewhere between 2 and 3. So this is the reason in this type of corrosion, they term it like iron 2 and 3. And this type they call iron 3. Okay. So actually, there have been a lot of research to detect the part of the passive film, which is ferrous oxide and also ferrous hydroxide, and they use a different kind of technique like Raman spectroscopy. And also they predict the crystalline structure and things like that. But the thing is, because ferrous oxide can get oxide easily in the air, so sometimes it is, if let's say you have a steel, you want to observe, is it true or not ferrous oxide exists on the surface of the steel, but because it gets oxidize easily in the air, sometimes it's difficult to be observed by the eye. So in the experiment, they try to do some experiment to create it, and then they think that yes, it's true, this ferrous oxide actually exists using the Raman spectroscopy, and then they detect the peak there. But definitely sometimes this kind of peak, the ferrous oxide, because it gets oxide easily, when they create this ferrous oxide, immediately it changes to the corrosion product. So sometimes it shares the same peak, but however, they still try to make an effort to do the study on this part of the passive field. And another is the ferrous hydroxide is also has a poor crystallization and also easily gets oxide when it exposed to the air. But this one, they have several methods, several publications. They use a different experimental condition to detect the peak. And of course, in this case, when it under the argon environment, they found that the peak actually shift to 260 and 407. But the rest, they use a Raman spectroscopy, and they detect that actually the peak is somewhere in the 500, around 500 something. And another one, and this is the passive field when go to the corrosion product, and this one they also detect, and they detected 306 and 538 and 668. But don't get confused this 538 with the previous one, because you think that okay, that one is 538 there, so this one ferrous hydroxide also 538. So then what actually is a different? How to differentiate this one, which is the iron 2 and 3, and with this iron 1 ferrous oxide. But you need to understand that this should only happen one peak only is 550. But however, to detect this one, Fe3O4, the Raman spectroscopy have to show 3 peaks. You have to show 3 peaks. If you show 3 peaks, which means the product that you detect is actually belong to Fe3 and O4. So another one, which is iron 3 and the last layer of this, the corrosion product, and this one they can detect it easily, because this one will continue to be there, so they can detect it easily with this X-ray diffraction pattern, or they can also using the X-ray photo electron spectroscopy to detect all these peak here. So to detect this one is not the problem. However, to detect this one is a problem is because they get oxide easily in air. So here I show you some example. For example, this metal here continuously to be exposed to the air that consists oxygen and water. So then you can see there's a mix of the like a dark red color and a little bit the black color and mixed together. But what happens if in the environment that's the content of the oxygen is very, very less, only until 0.5 ppm. So in this case, the color of the corrosion produced, this I did it in my experiment, it actually forms some kind of greenish and the white color. And they only form like this when the oxygen concentration is very, very less. And this green rust, they call it green rust, is actually consists of ferrous hydroxide and also ferric hydroxide. Okay, the ferric hydroxide is give the color of the greenish. But however, when this oxide is formed on the surface of the steel, and then you slowly let the oxygen gas to go inside this solution, and you expose this green rust to the air, and slowly it will change to the dark red color and a little bit the black color, same like the one the naturally formed corrosion. And they call this one is a mix of magnetite and magnemite. So now I'm going to brief you the passivation. So when you put the steel inside the concrete, okay, this is the concrete, okay, and the steel is inside. So how can the passive film form on top of the steel surface? Okay, now let us look at the composition of the cement that we use to make the concrete. And as known, the cement is actually made from 80% of the limestone and 20% of the clay, and they heat out this mixture as a temperature, very high temperature, like 1,400, around 1,400 Celsius, and they form the clinker. And this clinker inside actually composed of this alite, vanillite, and tricalcium aluminite and tetracalcium aluminum ferrite, and also with a little bit of sodium oxide, potassium oxide, and all this gypsum. Okay, and this is the cement clinker. And later they will grind this cement clinker into the powder. So this is the powder that you see when you mix with the water and everything to form this cement paste. So when the cement, when you mix it with the water, this edge is water, and they go through some kind of chemical reaction. It will start to form the C3H2H, which is called calcium silicate hydrate. And on top of it, it will form calcium hydroxide, or another technical term that they usually use in the civil engineering is called pollandite. Okay, and then for the part of the aluminite, when you add with the water and a little bit gypsum, they form the other component called estringite. Okay, and the small percentage of the sodium oxide and potassium oxide will actually react with the water and form sodium hydroxide or potassium hydroxide. And here I show you an example, and this is aggregates. Normally they call it aggregate because it's composed of the stone or big stone or the sun, all these things. So this is the air. So when the cement gets hydrated, and it will form this calcium hydroxide, which is this part surrounding the surface of the sun or the aggregate, or if this is the steel, then it will surround this. And then the CHH, which is this CHH, will actually in between all the aggregate, and this CHH is actually in some kind of gel form, which means like some kind of glue. They will start to glue all these things together. So at the beginning, you will have a lot of calcium hydroxide, and later slowly, this layer of calcium hydroxide will become smaller, and all of them will change to calcium silicate hydrate. It's like some kind of glue to glue them glue everything together. So this is what actually happened in the inside the concrete. So imagine this is the steel. So this will be one layer of calcium hydroxide surrounding the steel. Okay, and let's not go to the next slide. So what is the contribution of this sodium hydroxide and calcium hydroxide? And when you look at the pH, the table of the pH scale, and you know that if in the solution, if there exists a lot of this hydrogen ion, so then the pH will be very acidic, will go to from 6, 5, 4 until 0. But however, if in the solution you have a lot of this the hydroxide ion, then the pH of that solution will be very alkaline. So this is the reason when the component of the cement when they go through the hydration, they form this calcium hydroxide, sodium hydroxide, or potassium hydroxide, and this component actually contribute to the pH of the concrete, which is very alkaline. So when you have the newly made concrete, you have the pH around 13.2 to 13.6. It's because of all these components. And when you leave the concrete, for example, the building here for quite a long time, and then the pH will drop to this 12.5. And the very old concrete will reach to the 8 and 9. Why the old concrete will reach to 8 and 9? And you know nowadays the carbon dioxide in the air and are produced by our breathing or produced by the car, all these things, and this carbon dioxide will penetrate into the concrete and start to reduce the pH of the list. So what is the advantage when the newly made concrete have such high pH? So when the newly made concrete has such high pH, which is 12.5 and 13.2, which means inside the concrete exists this hydroxide ion, which is one of the components that is necessary to form the passive film. So this is the reason inside the concrete happen two mechanisms. The mechanism one is the because you know the concrete is a bit wet and they have a very layer a small layer of the solution on top of the steel surface. So what happens is the ferrous atom will get dissolved, and then this electron will move inside the steel and to mix the hydroxide ion, and this hydroxide ion will mix with the ferrous ion and to form the passive film. And another mechanism is when they mix the concrete, they will drag in some of the oxygen and very little oxygen, and this oxygen also will help to form this passive film. Of course, with time, let's say after 1 month or 2 months, or when the passive film form, perhaps the concentration of oxygen will be reduced. But somehow they still exist this hydroxide ion due to like what I showed before, the composition from the elite. When they get hydrated, they will contribute to all this kind of hydroxide ion. And this is the reason the passive film can stay on the surface of steel inside the concrete. So now I'm going to review the electrochemical technique that you can use to detect for example, the corrosion potential, or the pitting corrosion using all these linear polarization resistance. Another is cyclic potential dynamic polarization, electrochemical impedance spectroscopy. Another is a mode circuit analysis. All these you can done using the electrochemical techniques. And if you are in the laboratory, it's a small scale, and then you want to study the property of the steel that you have, and then how the steel react to the solution, and you can make yourself a small container made of the plastic, and here you can drill the hole and you put the steel inside, and then you have the reference electrode, and another is persistent electrode here. And another, you can make a hole, you can pump in this nitrogen gas to reduce the oxygen content in to expel the oxygen. And if you have the airtight cover, actually the solution inside can reach to this oxygen concentration less than 0.5 ppm. And here you can study a lot of things that you want to study by applying the electrochemical techniques that I mentioned here. All this kind of technique you can apply to it to study all this. And another one, if your steel is actually inside the concrete, and this is the setup that you should do, and you should put two wet sponge on top of the concrete and at the bottom to concrete, because the bottom one will act like the auxiliary electrode, and then they need the solution for the ion to flow through. So this is the reason you put the wet sponge here. And then the reinforced steel will be the working electrode. So then you connect these 3 cable, and then you will be able to study all the property that I showed in my slide before using the electrochemical techniques. So another thing which is important before I go deep inside is called Pourbaix diagram for iron. And this is very important because whatever potential you apply, and then together with the solution, the pH of the solution that you know, so you can more or less predict what is going to happen. For example, the newly matched concrete have the pH which is 13, around 13.2, somewhere here. So, and then this is the potential. If you apply the potential here, let's say here, this point, which means to the concrete, you will actually corrode the concrete. But however, if you apply the potential here, you passivate the concrete. No, passivate the steel. I'm sorry, not concrete, it's a steel. And then let's say if you apply it a bit too high, there's another thing called anodic reparation. And you will think that, okay, throughout this region, the steel will go to passivation. But actually it's not, because there's another line here, this diagonal line here is referred to is a potential where the water changes to the oxygen. I mean, if you apply after this line, from this line above, which means the water will change to the oxygen. So when the water changes to oxygen, because you know that oxygen is one of the components that is needed for the rust to happen. So if you apply the potential here, you think that, okay, I will passivate my steel. Actually, it's not. You generate a lot of oxygen, and the oxygen will actually cause the rust to happen. So this diagram is very important for whoever who study the corrosion of the metal. They usually have to refer to this diagram. Of course, this diagram I show you here is for the iron, but if you study like magnesium, then you have to look for the Pourbaix diagrams for magnesium and to see how is the relation between the potential you are going to apply with the pH. So the technique that I tell you, the first technique is called linear polarization resistor. So what is this technique provide you to know about the concrete? And this technique actually is called non-destructive technique. What does it mean by non-destructive technique? Because you apply a very small range of the potential. It's more or less like 10 to 25 millivoltage. So it's like you disturb your steel in a very small range of potential, and it doesn't destroy the steel. So from there, and you can know about, okay, if I put this steel in this kind of solution, what kind of corrosion potential will have this steel? And then of course you don't get confused with this corrosion potential and open circuit potential. Actually, they are the same. Because when I started this field, I thought corrosion potential mean that the corrosion happened there on the steel, but actually it's not. It's called the open circuit potential. It's the potential where you can see that there's a flow of this atom ion to form the passive film. But of course, if you disturb a lot from this range, then you will cause the corrosion. But if you just within this small range to study what kind of potential the steel have, then it will not actually destroy the steel. So from here, this part, and you can study the polarized resistance because when you apply this technique, you will get this curve, which means the polarized currents against the polarized potential within this small range. So from this gradient here, you obtain this polarized resistance, which is this equation, and from this polarized resistance, and you use this equation, and you get back the corrosion current. And so this you can get for the experiment. How about this B, this constant B? Actually, people have studied for a lot of time for the value of this constant B. And usually at the beginning, they will use 26 because they said 26 is when the corrosion is between 0.1 and 0.5 microampere, and they call it active state. But let's say when you apply this technique and you see that the steel actually doesn't get corroded, then the B, you have to change it to 52, because this means that the predicted corrosion current will be below 0.1. Okay, and this you only use B13 when it is in a very serious state and you see a lot of corrosion happen. So then you get this polarized resistance, and this B you put 13 to get back the corrosion current. So and another technique is called cyclic potential dynamic polarization. And this technique is a destructive technique. Why? And I show you two photos here. Because when you run this technique, okay, usually they start for negative 900, somewhere like that, negative 900. And the pH is around 13. So you go to this corrosion region, passivation region, and then you go to 500, something like this. Is a bit almost over the line where the water changes to the oxygen gas. And in this case, when you turn back again, then you actually destroy your steel. And then this is the reason you get a lot of corrosion. But if this is a destruction technique, why we use this technique to study what? Then you may be wonder why we need this technique. But when we use this technique, we need to figure out if there's for example here, whether there's any passivation zone or not. For example, this one, the pH is 8.2. When I apply this technique, I go there and I come back, it's more or less the same. And then at the pH 13.4, I apply the technique. For the negative one, I go to the positive and I come back, and this is kind of the curve that I obtain. But however, when I apply to 13.3, the pH, and you can see in some of the concentration, like 0.1 molar of chloride ion, I actually get this line that which is like stay there still. Okay, before I explain this line, okay, let us look at the axis that we have. Here is the current, the y-axis is the current corrosion current that we have, and this on the y-axis is a polarized potential that I apply. For example, I apply from here, I go out and I go down. So when I go to this point, I check what is my corrosion current. And I know that when I apply until this point, which is around negative 300 millivoltage, and actually I get a very minimum the corrosion current.
Excuse me, sorry, speaker. Can you use computer? Because the audience cannot see the pointer. The audience online cannot see.
Oh, the audience cannot online.
Yes,
so
yes.
I use this pointer.
Yes. They cannot see.
Okay. Let us look at this the A1, the graph of A1 pH 8.2. Okay. Let me explain to you, and we follow one of the curve. For example, this is the green curve, which is 0 mole chloride ion, which means there's no chloride in this pH 8.2. So if you try to trace the forward curve, which is the solid line here, and you can see that when you start to apply the potential, which is negative 900, the corrosion current start from here, and then the further the polarized potential go work more positive, and you can see the current start to drop, and then like reach the below 0.01 microampere. So this is good because of course we want to have less corrosion current flow to the steel. But however, when you continue to apply the potential toward more positive value, and you can see the corrosion current started to increase. And then later you go back again, which is the curve that shows the dot line. And then it go down from here and then back again. Of course, when you look at the curve of pH 82 and the pH 13.4, you will see that, okay, I get the similar curve. So what is the difference? If you tell me that pH 8.2 got the corrosion, but what happened to pH 13.4? The similar curve. But then you need to check the current, the corrosion current that induced on the pH 13.4. I applied the same range of the polarized potential. But however, when I apply it on 13.4, and you can see that the current induced actually is much less than the one that happened at the pH 8.2. And you can see at pH 8.2, the current can go to 100, even 10,000, no, 10,000, yeah, 10,000 microampere, which is very large. And if you have the high corrosion current, it means that corrosion is happening. But this, because he have the small corrosion current, so which means at pH 13.4, actually there's no corrosion happen. And then now let us compare 13.4 with 13.3. And also whether you can see my pointer. Okay, and you can see at different kind of concentration of chloride ion, they come up a curve that which is a little bit different, especially this one at the 0.1 molar chloride ion, and also another is 0.25 molar chloride ion. And you can see that here, the curve actually, even though you apply this range of the potential, which is start from the negative 200 to 200, you can see that the corrosion current, and also whether I can hide this one. Okay, yeah, I can hide it. Okay, you can see that the corrosion current doesn't increase. They still stay there around somewhere between 1 and 2. They stay there. So what is this reason about? And this reason actually is called passive reason. Let me go to the next slide. It's called passive reason. Okay? Which means if you apply the potential within this region, the passivation will happen. But however, if you apply more than this region, suddenly you can see the current shoot out like that. So I go back to this, you can see the current shoot out like that, and this is the current. Suddenly, at this potential 200, even you just stayed at 200, but you can see the corrosion current actually increase tremendously, go to 100 and 10,100. This means at this point, this is called pitting potential. And in this pitting potential, and this is the passive reason, and when pitting potential happen, and in my previous slide, I saw you when it comes to the pitting potential corrosion, actually the corrosion will go deep, like one point there, like apple at the one point, but they go deep inside the steel. So this is called pitting potential. Even on top of the surface, you don't see that there's a corrosion, but actually there is, but it just go deep inside, like what I explained in my previous slide about the types of the corrosion. So when you go back again, when you try to force the applied potential to go back to this, and then of course you can see the curve will go down like this, which means they try to impede the corrosion from happening. Then the curve will go in this way. And then you can see this kind of, the existence of the passive region, like what I saw here, this passive region actually depend on the pH of the solution. If you have the pH which is 13, and you have the wide range of the passive region, but if you have go down to the pH 11, the range becomes small. Because when you refer to the provide diagram for the iron, and you can see when you go to the 11 here, you can see the passivation region becomes small. And then when you go to the pH 7, almost like there's no passive region. And go to the pH 5, it's almost nothing. So this is the relation between the apply of the applied potential with the pH. And this technique called, like what I said, tell you here, cyclic potential polarization allow you to see this kind of curve, where it happened the passive region, and for the engineering to decide when they should apply the potential. For example, if you have the corroded steel, I mean, if the steel is not that corroded, but you want to repair it, then within this pH of the solution that you have, then you need to know in which region of the potential you need to apply. And when you have this curve, you know that, okay, at this region of the potential, I need to apply so that the steel will get passivated. But however, if by chance you study, you found that the pH of the solution in the concrete is down to the 9, then you know that the applied potential has to be in this region. Very, very, very small region here. You cannot apply here, because if you apply here to the pH which is 9, you actually, instead of you repair the steel, you corrode the steel. Okay, and another technique is called electrochemical impedance spectroscopy. And these techniques actually allow the resistance of the passive film to be studied, to be measured, so that you know, okay, if there exists a passive film or what. And this technique, when you apply for any, and you will get 2 blocks. One is a Nyquist blocks, another is a Bode blocks. And in these Nyquist blocks, usually in the academic study, they hope that you block it in the orthonormal axis. What is mean by orthonormal axis? We mean you put the same scale on the y-axis and also the same scale on the x-axis, and then you will see clearly the curve that you get is actually semicircle. Okay, and another part to calculate the Bode blocks for Bode blocks, and they use this impedance, the modulus of the impedance here, and then go against the frequency, and this is the angle, the phase angle, and you can calculate using this equation to get this. Okay, so from there, and then you need to work out a circuit to fix it, and this you can, it's some kind of modeling, and there's a software to do it. Okay, but usually when it comes to the steel bar and with the passive film, with the electronic, they prefer to use this kind of circuit to fit it instead of Landau circuit, because Landau circuit is very general. It only consists of the RS, which is the electronic resistance, and you can get it, and this is the capacitance, and this is the resistance, provided that your system, and you know that is a pure capacitor, then you use this circuit. But unfortunately for the steel bar, because the passive film is not homogeneous, and then it's a bit porous, and together with the existence of some electronic some solution surrounding the surface of the steel bar, so this is the reason they prefer this kind of circuit to model your curve. I mean, to model this curve. So when you model this curve and using this kind of circuit, and you will be able to know the resistance of the passive film or the resistance of the charge transfer between the steel and the electronic. And from here you can see, if you have the very high, let's say very high resistance of passive film, very high value, and which means you have the very good passive film, which means the steel will not get dissolved easily. But however, this RF value is very low, which means you have the very low resistance, which means the ions can pass through this passive film, and then which means the chloride ion will go in and pass by, and then they will corrode the steel bar easily. And this is the reason they use this technique, which is called electrochemical impedance spectroscopy. But when you model, when you apply this circuit into your system, and you will get another value called psi square. And this psi square, usually they will have the value of 3 and 4 as an order of magnitude. And if you have this value, this proves that you actually get the proper circuit. If not, then you might need to change to another kind of circuit, and the software itself will tell you, or you can read through any kind of publication to see the complicated case. But usually this is the general case. Okay. And another is called mode socket analysis. And what is this mode socket analysis about? Actually, when you apply this technique, this across the steel surface from the negative 80 to plus this 700, and you will get back the capacitor. And this is the equation to calculate the capacitance, but at this moment, I will not go deep inside. And let us look at the equation itself. And if you get the curve like this, which is the positive slope, which means you actually have the donor charge, which means it's an electron who actually flow through the system. But however, if you get the curve like this, which you have the negative slope, which means you actually, the charge carrier is an acceptor charge carrier, which means the hole is flowing through inside this circuit. And this kind of the combine of the positive slope and the negative slope, and you will get it when you study the stainless steel. But however, if you study the cast iron steel or the normal, the carbon steel, you usually will get this kind of curve. Okay. So the same thing is from the slope here, this is M is the slope. You get the value of the slope, and you plug in here, then you get the ND. ND is the concentration of the charge carrier. If you have the very high charge carrier, which means the resistance is lower, which means the passive field has a lower resistance, because when you have a lot of charge carrier, which means you have the electron flow through the steel. And if you have the electron flow through the steel, and you know that the corrosion current is high. When the corrosion current is high, which means the resistance is low. Okay, if the resistance is low, the corrosion resistance is low, which means the steel will get corroded easily. So from here, you can work out the thickness of the space charge layer for this equation, because here you can get the value from here. No, because first you get the value from the slope here, and from this slope you get this ND, and then from this ND here, this is the concentration of the charge carrier, and plus the potential that you apply, and this is a constant value, so you get the thickness of the space charge layer. Okay, and there's a report saying that if you get this value, for example, at the potential which is 0.4 volts, which means 400 millivolt, and you get this space charge which the thickness is around 1 nanometer thickness. Then in this case, 1 by 4, and you will get like 4 nanometer. And this 4 nanometer is referred to the thickness of your passive film. So this technique called mode socket allow you to study the thickness of the passive film. And just now, the one that this electrochemical impedance spectroscopy allow you to study the resistance of the passive field. So all these electrochemical techniques, and if you know very well, and you can apply it, and you can study the property of the steel. Okay, another thing you don't forget, if you still remember in the slide I talked about the technique that we use to study the electrochemical and we use the reference electrode. And there's a different kind of the reference electrode. There's the plata chloride and calomel, and this the copper sulfate, and all these kinds. So when you read the article, and you need to know which reference electrode they use. If they use this one, and in your lab you are using this one, then you need to convert the value of this to this one. And there is a table to convert it. And now on the internet, and you also can type in, then there will a link, and you just put in this number, they will convert it for you, because they have equation in the online website, and you can find the conversion table. They will help you to convert. But for example, here I show you the very simple one, and usually this SHE is a standard one. So people always refer to this standard. So you can see in the provide diagram for iron, they actually use HHE, which means standard hydrogen electrode. So in my lab, I actually use this silver chloride electrode. So this silver chloride electrodes, because this table here, they're using HHE. So when I use silver, I need to do the conversion to see. For example, if I get like 0 here for this, is a passive result for this electrode, which is HHE. But however, when I use the this is silver chloride electrode, the value is actually 0.197, or I round it like 0.2 voltage to show in my result. It's actually the passive result, not the passive result of the standard hydrogen electrode. Okay. And now I show you some of the example of the work that I did, the publication that I have here. And this one, I studied the pitting corrosion on this high strength, high carbon steel in very high alkaline deaerated. I use deaerated because I have pumped through this nitrogen gas to remove the oxygen. Okay. And its high strength steel is because the carbon reached 0.82. And the normal steel is 0.2 to 0.4. This is the cast steel. Okay, and this is the cross section surface of the high steel, high carbon. And you can see when I apply this open circuit potential, and I detect, and using at this pH 13.4, and also because I have pumped through the gas nitrogen, so the oxygen concentration is very, very less. It's almost close to the one that inside the concrete. And then I add in different kind of the concentration of the chloride ion. And you can see at 1 mole, when I detect the open circuit potential, is very, very much different from 0.5 and 0.25 and 0.1. And in this 1 mole, because there's a high concentration of chloride ion, and everybody know that the chloride ion is an aggressive ion, and it's an ion that will break down the passive film. So you can see, and it goes down to negative 8. And you look at this provide diagram for this. Okay, this 13 around pH 13, so I 13.2. So I go up here, and you can see it go to the negative, which means it's moved toward the corrosion zone, which means there's a possibility that the corrosion will be happen when exists a very high concentration of chloride ion. But however, when you have the very little this concentration of chloride ion, the open circuit potential will stay still somewhere around this region. So which means your steel still remain passivation. And then this is the cyclic potential polarization, the technique that I apply. I apply to 0.1, 0.25 until 1 molar. And I can see all of them seem, when they come back, the curve still the same, still in the passive region. I mean, they don't show this kind of pitting potential. But however, when I apply the 2 molar chloride concentration and 3 chloride molar concentration under the same solution, the pH 13, and we deaerated, even without oxygen gas, and you can see when you apply from here to here the potential, and you can see the corrosion current stays still. It doesn't have anything happen. But suddenly, for this 2 molar chloride concentration, when you apply until 400, and then suddenly the corrosion current shoot out, which means here the steel get corroded a lot. So when you return back, like you try to dump the corrosion potential, try to stop the corrosion potential, and it go to the very large curve here. And when you go to, when I apply 3 molar chloride concentration, and you can see for the 3 molar chloride concentration, when it reached somewhere like 100, and suddenly this corrosion potential shoot out much more earlier than the 2 molar, which means the higher concentration of the chloride you have in the system. I mean, 3 molar of chloride concentration is a lot. Usually, to reach for the steel inside the concrete, to reach this one, it will take years and take a lot of this the correct concentration to penetrate through inside. So you can see even under the pH, the neutral pH, which is very high here, the one that I use is pH 13.4, and without the oxygen, if you have the very high concentration, super high concentration of chloride ion, the steel will actually get corroded, and you will have the very small range of the passive resin. And this is the reason in the laboratory people study this, so that you have a better idea to be able to apply it when come to the field site. And here, as I said before, from 0.1 to 1, they have this kind of passive region. And in this region, you don't see any shoot out of the current. So I take this region as a passive region. So then I apply the anodic potential, a constant anodic potential. For example, 0.1, I apply very high, plus 10. Plus 10 is here for the 0.1. Plus 10 is very high. This the polarized potential. And 0.25, I go to the 0, and 0.5, I go to negative 200, and 1 molar, because the concentration is very high. So I apply it close to the negative 350, and apply it for 48 hours. And you can see, if I apply very like for 0.1, and with this plus 100 millivolts, and apply, and within the 2 hours, actually you passivate the steel. But however, if you apply continuously to 20 hours, you actually, and then instead of passivate the steel, you corrode the steel. So in every concentration, every pH and every concentration of the chloride ion, and you need to be careful to choose this polarized potential you need to apply in the anodic reparation. And also you need to be careful with the amount of the time that you should apply on the steel. Because if you apply too long, you think, okay, anyway, it doesn't matter. I leave it for 30 hours, because if I leave it, perhaps the steel will get the better passivation. But actually it not. Instead of get the better passivation, you actually corrode the steel. So all these things, of course, all these things, sometimes in the field, the engineer has to bring it to the laboratory to have the proper understanding what is going on, what kind of potential they should apply with this kind of corrosion inside the concrete, and all this knowledge they have to found it properly and look at it properly before they apply the anodic reparation. And of course, here is the curve that I built. I found that, okay, if I have the pH 13.4 and I have this kind of chloride concentration here, and then let's say I have the chloride concentration 0.1, then within this range I can apply my potential with no pitting corrosion. But above this range, for the 0.1, if I apply this range, then the steel will get corroded. Of course, when the concentration of the chloride, the higher it goes, the range becomes smaller that you can apply. So this is the study that I have performed for the pH 13.4 and for the steel that which is high stress steel, high strength steel. It's not for the normal cast iron steel. For normal cast iron steel, if you know about it, then you need to apply this technique to study it properly. Okay, and here I can see when I apply that time, I see the gas on the surface of this steel. Then I I go through the literature review and realize it is a hydrogen gas. So here I try to depict why the corrosion happened. Okay, inside the concrete. At the beginning, with the presence of the chloride ion, and on this, but at the beginning, the passive film will form here. Okay, and because of the chloride ion, and this chloride ion will actually weaken the passive film, and then later on, it will break down the passive film, and the chloride ion will go inside this, and with a little bit of the electrolyte, the solution inside, and then the passive film will get thinner and thinner, but they still form, but get thinner and thinner. But later, when inside here, but because the atom ion will get dissolved, will form this electron, and this electron will react with a small amount of the water, and it turned out to become this hydrogen gas, and with the hydroxyl this. And this hydrogen gas actually will react with the CH, with the chloride ion, and then to make inside a little bit more acid. So this is the prediction that we will have. Of course, other people have other version of the predict, and based off the observation that they have in the experiment, and they can start to predict the model how this thing will happen. Okay, how the corrosion will happen in the deaerated the solution, and this is how I try to explain why this thing happened in my system. Okay, and another paper that I have produced is called Measurement of the Hydrogen and Emprisonment of the High Strength Steel. And in this experiment, I generate the hydrogen. So and to see how the hydrogen penetrate into my steel. And here, and we have the cell here, and this steel we cut in this shape and then put inside here. And here we fill it with the electrolyte. And I apply, as what I said, when you refer to the Provide diagram for iron, and I think this diagram is very important. When I apply the potential here, below this diagonal line of this, where the water is going to change to the hydrogen gas, which means if I apply the potential here, I'm generate the hydrogen gas. Okay, and this for the people who study the cathodic protection. I mean cathodic protection, which means you tend to apply the potential more cathodically when you refer to the open circuit potential. When you apply here, but if you don't apply carefully, you apply more than this diagonal line, and this is where the hydrogen gas is going to produce. Okay, so when the hydrogen gas produced in the electrolyte, what is going to happen? So here is a fracture surface of my steel. I break it in air, and then I study using the scanning electron microscopy, and I can see the fracture is like they got the void and the hole here, like a sponge inside this. This is the fracture surface of the steel in air without exposing to the hydrogen gas. But what happened when I expose it to the hydrogen gas, and I can see this is the circumference of the steel, and you see that the cracks start to happen from here. Because if you compare from here the circumference is very clean. It's very clean. The steel just break like this and without anything. But however, if the steel break with the assistance of like hydrogen gas, you can see actually it came from the asphalt and go deep inside. And when I examine the surface, I can see the surface fracture is totally different. And you can see there's the hole here, the cavity here. And this should be the reason where the hydrogen gas enter into the steel and cause the steel to break under abridgment condition. Okay, and another SEM graph that I show you, you can see the crack is very different. So from here you can see that this should be the place where the hydrogen gas enter into the steel, because when the steel break under brittle condition and it break very fast, it doesn't resist anything. It's like the glass, you just break, bang, just like that. Okay. And another study is I studied the possible using the You know, nowadays people talk about recycle. Okay, recycle using the recycle product, and in some of the solution that discharged by some of the industry, they contain a very high concentration of chloride, sodium chloride. But as known, the chloride ion is an aggressive ion. It will break down this passive film. So either we recycle the effluents to the clean water, or maybe we think that we can reuse again inside the concrete, and to see what is going to happen to the steel if we reuse this kind of a solution with a very high concentration of sodium chloride. And in this case, actually, the concrete itself, the cement itself, I mix with different kind of the pozzolanic material. For example, here, first, this is the Poland cement one. Is a common cement that used by everybody. And later in this cement, I add in another, this is also the industrial waste called free ash. And another is a silica film. And another, this is the cement, and you add with the slag. And this one is 8% for the silica film, and free ash is also, I add in 8% of the this. But this one, because it's a commercial product, they have the copyright, and they found that this they mix with this, they found it better than the cement one. But of course, I don't know how many percentage they use in this cement 3 slag. Okay, so I just take it, and so I put in the set amount like the cement one. So then I study all this kind of composition. What is it to do? Whether it helps to reduce the corrosion or not. Of course, before that, I also studied the structure using the SEM, and I see that the Poland cement have irregular structure, same like the slag have the irregular structure. However, the free ash and the silica film, actually they form more like a ball, and when you zoom inside, you can see they compose of very, very small, tiny ball. And then of course, all this kind of thing, all this kind of structure, actually they will influence the mechanical property or the flowability of the concrete, because the concrete, before it get hardened, it need to flow. For example, people study self-compacting concrete, and all these things they need to know very well. Of course, the addition of this free ash and slag and silica film, they have another property. What is it property? They are called pozzolanic material. Why they are called pozzolanic material? Because they will react with the calcium hydroxide and transform it to the CHS. Because the calcium hydroxide will be produced in the Poland cement, as I explained before in my previous slide. And then the CHS will be act like a glue, which means this product here, free ash, slag, and silica film, will transform calcium hydroxide to form CHS, which means there will be more glue formed on the inside this concrete. So then I apply all the technique that I explained to you, the corrosion potential, and to study the technique. And I can see that if you look at this, the green line here, this green line here refer to the cement 1 plus 8% of the concrete, 8% of the silica film, and this one I add 5% of the chloride ion, and another one if without the chloride ion. And you can see the one with the chloride ion, the green one, which is formed like the dot here, they will have the more negative potential. And without the chloride ion, actually they have less negative potential, which means it's better. Which means this is the result of the passive film, where the passive film happens. And then another one is the cement 3 slag, and this one without this chloride ion concentration. And you can see the corrosion potential is more positive, which means fall into the passive region when you refer to the provide diagram. And also they have the less corrosion potential, and using the technique that I explained before, how I calculate this. Okay. And then when I try to plot the corrosion current and with the potential current, and for the 28 days, because usually they cure the concrete for 28 days, they cover it with the moisture. And later I studied another 250 days. Okay. See, there's a lot of mixtures here. So just let us focus on the one that of the cement 3 slag with 5% of chloride. And the other one is without the chloride. And you can see, compared to the one of the cement 1, which is the Poland cement with 5%. And here is the place where the cement 1 with 5%. And the cement 3, the slag 5%, the corrosion current is more or less same as the cement 1, almost like between 1 and 5, something like that. But of course, at the different corrosion potential. But when you go to the 250 days, and you can see the corrosion potential of the steel inside this cement 1 increase. Like what I said before, when you have the higher corrosion potential, which means the steel is getting corroded, which is not good. But however, the steel that emerged in the cement 3 slag with 5% chloride still remain the same. I mean, it doesn't change, which means the slag actually plays an important role to prevent the corrosion. Of course, if you look at the cement 3 slag without the chloride concentration, you can see is they actually have a very less corrosion potential, and also they have very less negative the corrosion potential as well. And then after 225 days, the one that without the correct concentration for the cement 3 slag still remain at the same place with very less corrosion current and very positive corrosion potential, which means they are very sure that they are in the passive state. But you can see the one that cement 1, and even though without this correct concentration, they actually move out already after 250 days. They move out, go to the high speed corrosion region. Although at the beginning, the cement 1, after 280 days here, you can see they are actually in the passive state. But after 255 days, the one already go out. But which means the cement 3 slag got some property that actually help to prevent the corrosion, even though you add in a very high concentration of the chloride ion. So here we study the mass loss. The mass loss here is referred to the steel. How much the steel lost his mass due to the corrosion. And we can see that, okay, if you look at this, the solid orange one, the solid orange one is with the 5% of the chloride. And you can see, actually, the steel that embedded in the concrete contains cement 3 slag. They have less corrosion because the steel lost very little mass here compared to the one of the Poland cement, and which means this cement 3 slag has actually can prevent this high concentration of the chloride ion, which is 5%, to corrode the steel. And also silica film, and better than the Poland cement one, and free us also better than this cement one. But the best one actually is a cement 3 slag. Okay, and when I calculate the corrosion rate, and I see the same thing. If you look at the orange one, which is with 5% chloride ion concentration, and you can see that the free us is the second one, and the third one is the silica film, and the best one actually is the cement 3 slag, which means cement 3 slag has the corrosion rate which is less than actually even the cement 1 by itself, which mean actually we can use the high concentration of the sodium chloride in the concrete. I mean, the industrial waste which contain a very high concentration of the sodium chloride in the concrete that contain cement 3 slag, because this cement 3 slag have the less corrosion rate. And this is a very good discovery. I mean, instead of sometimes we recycle the industrial waste, it can cost more money than when we use it. we find it somewhere else to use it. And we can see that in this case, when the 5% of chloride concentration, when we use it with cement 3 slag, and it has a corrosion rate is much more lower than the cement 1 with this 5% chloride, and even lower than the cement 1 without 5% chloride ion. So which means it is possible to just use directly the industrial waste that contain the high chloride concentration and with the cement, but the only thing is had to choose the proper type of the cement to be used. Okay, and here I would like to end my presentation, and I hope that you all learn from it. Thank you very much.
We have question from the participant online. Okay, Mr. Shahrul Fitri.
Shahrul,
Yeah, this one.
Ah,
You can read the
okay.
question so that all know what is the question.
Okay. Good morning, Dr. Metal liver in RC structure can be corroded by carbonation and chloride attack. Your slides show that carbonation reduce the pH to X. That will trigger the destruction of passivation layer. How chloride destroy the passivation layer of steel? Does it also reduce the high alkalinity? No, the chloride actually doesn't reduce the pH. The chloride doesn't reduce, but the thing that reduce is CO2. Of course, if you have the CO2, let's say you have the CO2 and enter into this the concrete structure and it reduced to the pH 8. Okay, imagine it reduces the pH. But if without the chloride ion, perhaps the steel can still last for some time. But however, if with the pH is so low until 8, and with the presence of the chloride, and the chloride actually can also penetrate more into the steel. I mean, which means when you reach the pH 8, the passive film doesn't fall on the steel, and which means you don't have the defense anymore. Which means your enemy is chloride ion. So when you don't have the defense, so your enemy can just enter so easily into the steel. Into the steel because when one of the slide I show you this in the pitting corrosion. I mean the very very early slide. The pitting corrosion. Let us go to that. The beginning. Where is it? Okay. The pitting corrosion is because of the aggressive iron, which is chloride iron.
The online cannot see.
The online cannot see. Okay. Then I go to this. Okay. If you look at here, it's because of the pitting corrosion happen is because of the aggressive iron, which is chloride iron. But if you go down to the pH edge, which means you don't have this defense anymore. I mean, this line of the passive film, you don't have it anymore. Which means the chloride ion can just enter so easily into the steel, and then will cause the corrosion there. So this is the difference. So don't get confused. The chloride ion doesn't decrease the pH. Okay, the chloride ion is some kind of like an enemy going to attack here, and the pH. When you have the higher pH, you form the passive film. You form your fortress. Okay, you have the defense here. You have the wall here to defend the enemy from entering into the steel. But however, if the pH drop to 8, which means you don't have this defense anymore. So the enemy you get already torn down, and the enemy can just enter so easily into the steel. So I hope you understand my explanation. So there are two different things that you need to look into.
Okay, another question. Does rust on embedded rebar in PC?
Does rust on PC will affect the dielectric property and magnetic property? Yes. Sometimes people also study this, and I have some result on that, but I have not analyzed it. Which means I actually form the rust on the surface on the steel, and then I go through the chemical technique. I mean, I apply the electrochemical technique on this the rebar contain the rust, and to see whether this rust can actually have different dielectric property or magnetic to protect the this. Because in some of the cases, people think that the rust, let's say the rust form on the surface of the steel, they can also act as a protection, but it's a temporary protection. It's not the long-term protection for the rust, but perhaps they can have some effect also to protect the steel. And then in this case, of course, the property will they will be different. They will be different from the passive field. Of course, people still prefer the passive field, but somehow the passive field sometimes, like I said, the old building, when they go to the become old, perhaps the pH will change, so people mainly focus on that. But they still have the research. They focus what happens if the rust form. I mean, cover the whole area of the surface. Yeah, they think that the rust still can act temporarily as a protection, but not the long-term protection, because the rust itself is very porous. It's very porous.
Okay, we have another question from Dr. Raizam for Chem 1 or Sem 1.
Sem 1 Prafi assistant. Why does the mass flow remain relatively high despite the addition of the free ash? Does that relate to delay pozzonamic activity or permeability? Okay, this is a good question. Okay, one thing you need to understand, in this study, I only apply 8% of the free ash. Okay, of course, in this study, I apply 8% of the free ash, 8% of the silica film, and the other. Of course, there's another study, people just mainly focus on the free ash. They use like 1% or 2% of free ash, 3%, 5%, and they study the whole range of the percentage of the free ash. But this doesn't mean that, okay, you apply 1% of the free ash will have the same effect at the 8%. Maybe at the end, in this case, I need to apply maybe 10% of the free ash to have the same effect. To have the same effect, like so that the what is the question? So that the
delay
delay. Actually, maybe there's a delay of the pozzonamic activity or permeability. But however, this also influenced by how many percents that I apply. Okay, so some people have gone through the a series of studies, like what I said, just mainly focus on the free ash by applying different percentage and different percentage under different conditions to see, okay, whether if I apply this percentage, they will get the same effect or not. But actually you need to understand this free ash, although it's a pozzonamic material, it will change the calcium hydroxide to the CNH. Perhaps sometimes how to say, sometimes you apply too much, actually not all of them being used. Okay, so what happens if when not all of them being used, so actually the effect will just, how to say, stay there. Maybe you apply like okay, the water vital pressure 0.5, and you start to apply like 10%, 15%, 20%. Perhaps this 0.5, the water and vital ratio is only enough for 15%. So when you have 20%, the other 5% is like you just leave it there. I mean, you don't really use it there. Okay, so it is nothing to do with the delay of the pozzonamic activity. But if you want to study the delay of the pozzonamic activity, then you need to compare it with the silica film and to have this the whole series of the study, and you make a comparison. But here in this case, in my case, it's difficult to say if there's a delay or not, because I subjected all the things under the same condition.
Okay. Last question from the same Mr. Shahrul Fitri.
Thus, the result will be similar if we apply the accelerated corrosion step. Okay. And you need to understand why in the laboratory people apply the accelerated corrosion. Okay, of course the result will be different. When you apply accelerated corrosion. For example, I have one of the study in the laboratory because it was requested by the company, and see, for example, you know, for a building with the concrete and with the rebar inside, it will take 100 years to collapse. Of course, in the laboratory, we cannot wait for that long. I mean, we are not going to live for that long to obtain that knowledge. So in this case, people apply the accelerated corrosion. Of course, it will be different. Will different. The result that you get will be slightly different. But when you apply the accelerated corrosion, it's because you want to shorten the time. You want to see the result. You want to shorten the time. Of course, some people they do two study. One is the accelerated one, and another one, and they actually live it there for years. For example, my boss before, and she retired already. Actually, she had the concrete who lived there for 20 years. 20 years, as long as she was working there to compare this result with to leave the thing for that long and with the accelerated corrosion, and they can do kind of compare study. Yeah.
Okay, if there are no other question, any other question from the audience? Okay, if there are no other question, we are going to wrap up this session. And I would like to thank the speaker for the interesting and comprehensive presentation with regard to the steel corrosion, preservation, and electrochemical techniques. Thank you again, Dr. Lee Xiaopun.
Yeah,
We brought her from Spain, coming to Malaysia. So thank you very much. I would like to call our head of division, Dr. Raizal, to give our token of appreciation to the speaker.
Thank you very much.
Again, that's you. Okay.
Yeah,
The camera is here.
Yeah.
I'm going to take photos. Also, can you take photo because my phone is almost full. Okay, three of you, then yeah, three of you, and then after that, the two of you. Okay, let's take photos. Wait. Okay, I'm going to use this one. Okay, smile. 1, 2, 3. Okay, thank you so much. Another one. With speaker only. Okay.